So good day, I'm Justin Gabriel Arlegaspian. Today I'm going to present my work on predicting loan approvals using machine learning. So this project takes real-world data, challenges, and compares 10 machine learning models to provide the best solution. So real-world data is messy, so there's a lot of missing values, missing input fields, inconsistent credit scores, typos, you name it. So that's why in this project, we introduced 10% missing values to simulate just that. For us to build a machine learning model that handles this chaos while staying accurate and fair. So the base reference for this project uh is a project by Abuelov on Kaggle. So first, so the main differences or the main improvements that we've worked on is that he only has three basic models tested. Use a clean, perfect data, which is unrealistic, of course. And he did little to nothing pre-processing steps. So that's why in the project that I work on right now, or the project I did, I provided ten machine learning models. We've intentionally injected realistic imperfections, and we developed a comprehensive pre-processing pipeline to ensure that a fair comparison. So moving on to our pre-processing, we first have the separation of categorical and numerical columns. So first we separated it. Why? Because they require different treatment. So numerical data is like income or scores that need scaling, and categorical data requires encoding. So the next step of preprocessing is to split the data set. So we split it with 70% for training, 15% for validation, and 15% for testing. Next is the creation of pipeline. So in this, we created two separate pipelines, the numerical and the categorical pipeline. So numerical pipeline imputes missing values with the use of standardized, while categorical categorical pipeline imputes the missing values with the use of one-hot encoding. So lastly, we have the column transformer. So this is a powerful tool that automates with this workflow. So it supplies the transformations to the right column, saving us from manual errors and measuring consistency. So this is also where our main train and test data is going to come from, X-train process and X-test process. So I've run through the models close together into a single table so we can properly see what ranks the highest among the models. So we can observe that CatBoost is CatBoost sits at top one with a 93.1 accuracy, 0.93 PR AUC, and 0.90 precision. Then we have random forest following it and gradient boosting following it. So why did CatBoost sit at the first one or ranks the highest? So CatBoost has a native system that handles missing data. So it doesn't need any imputation guesses. And it also has a categorical feature optimization, so it understands raw data text more properly. And it also has overfitting resistance. It stays reliable that means that it stays reliable even on real world data. And as a conclusion, with 93% accuracy, with native handling and real world imperfection, CatBoost sits at top one. And this also means that pre-processing, also concluded that pre-processing really affects the quality of the models and how we can handle or we can provide proper output. That pre-processing is a step that we shouldn't hinder or take lightly because it really affects the outcomes of our models. So that will be all for my presentation. Thank you for listening.